Hythloday response video. I might do this in a couple of parts because I just want to go through some of these. To try to explain these details, because apparently there's just no capacity to understand the distinctions being made. And I can say it over and over. I can say something like, it's a one-dimensional elemental particle. And that just doesn't mean anything. That's like saying hyperboloid to these people. Even when you draw it, really simple, like, it's an arrow. And the arrow can't move two ways. It can only do this. It can't collect anything. Alright, so I was thinking, so to understand, that's these tons, okay, they're light, they're magnetism, they're gravity. They're all the forces. That's what they are. And then the other things, you don't even have to think of them as made of them, but they are, I think. But they don't even think of it that way. Protons, neutrons, electrons are round things, hard things. And what those hard things can do is they can absorb an arrow and hold it for a while. And the consequence is they have to release something in the other direction. So they can take one way and they release one some other way. They exchange them. And that's fundamentally all there is. So there's just arrows, and there's little round things that exchange them. And they exchange them, again, now I have to add color, in two forms. The electron is a round thing that's takes in arrows of one color, releases arrows of another. The proton does exactly the opposite. There. Those are the principles. Those are the axioms. Those are the rules. Not too many of them. I mean, I could go into the speed of light thing, the straight line thing, but I'm just saying the arrows are the fundamental particle. The electrons and protons are fundamental. I mean, they're made in some old circumstance, but they're not elemental. So they're fundamental, but not elemental. This is the element. This is really hard-baked bread or something. Okay, it's not going away. Like a really old gingerbread house. Just nothing will eat it. So it's hanging around. And the key is that these things can possess these things in a disposition. That is, they can have more going one way than another way. Not much more, but more. And the real key thing is these arrows can be trapped between them. They can be stuck in patterns. If I had, say, 4 of these ones, the point would be is they could actually be cycling a whole bunch of them in a orbit. Alright, so they could be pumping them in a direction, like electric current, for example. And depending on how they did that, like at the closeness, they could have 4 of them on one side and 2 on the other side. That disproportion would mean the object would gain something called velocity. But the real point is these overall, you would take a net value. If you had a group of these, you'd take a net value. They got so much pressure going one way, so much pressure going another way, so much pressure going the other way. And it's the net value that is their velocity, so to speak. Alright, but they can hold velocity. You can sort of get the idea they can have arrows in them. See how these arrows, you got one going this way, you got one going this way, you got one going that way, you got one going that way. And of course it's in 3 dimensions, so there's this way and that way. So they can have arrows in the 3 dimensions. They can have a net this way to this way, a net this way to this way, and a net this way to this way. They can have 2 extra going this way, they could have 1 extra going this way, and they could have 1 extra going that way. And then they would have an overall movement of this way. The arrows can't do that. No function. So I'm giving you a mechanism. I'm telling you why there's a difference between these things and this thing. A fundamental difference. And I'm explaining to you that, consistent with my theory, gravity and magnetism and these other things, you don't speculate about them gaining momentum. You sort of understand that it wouldn't make much sense to think of them that way. their whole function breaks down if you gave them momentum. No one talks about gravity wobbling or waving in any realistic sense inside of a system. I mean, they talk about gravitational waves, but we know there's no there's no waving of system dynamics in that manner. So I won't even bother with that because the stupid wave word is just so annoying. Alright, so I just wanted to get to this. So here's a simple way of explaining it. So the space shuttle thing, it's sitting there looking like a penis, just sitting there with its little rocket. And so before it launches, it has electrons that just have a little bit of stuff between them. Well, that's not a very good drawing of a little, but okay. Little. Just put L for little. Alright. Now all this rockety shit happens. Boom, 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 boom. Lots of force being pushed. So lots of arrows going up. Lots of arrow pressures. Arrows. Okay, there's lots of arrows going down, but they're reflecting off the ground, so they're going back up. And blah, 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 blah. Lots of arrows going back and forth. Blah, 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 blah. Those arrows go into the rocket. Okay, and where they're going is in between the electrons and the protons. So in between the electrons and protons, it's collecting all of those arrows. All of those arrows. All of those arrows. Arrows, 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 arrows. So it's getting thick with arrows. Now, it's not getting thick with actual mass because the atomic weight is still the same. Same number of protons, neutrons, and electrons. Just increased in the empty space between them is getting thick with these force arrows. So it's collecting the force arrows. So it's full of force. It's not full of anything other than these arrows in the form of force. So the force is conveyed from the explosion of the chemistry into the spaceship, and the spaceship now has a velocity because it's collected the force. It's full of force. And it will, because of that, it'll just keep collecting it as it keeps shooting stuff out, collects more and more force, keeps collecting more and more force, and then it gets to a maximum speed, and then it hits some sort of barrier, like it stops propelling itself, and then gravity, the force arrows from gravity start pushing down on it, and so it might lose some of its force arrows. These arrows might get knocked out because these arrows are the opposite arrow. They're going to create losses of the net balance. They're going to change the net balance. And then it might get to the empty space where there's a lack of this gravitational imbalance. That means the same number are hitting from the top and the bottom, so there's no reorientation of the force, and so then it'll just maintain that velocity forever because it's got the force arrows in between the fundamental particles, and they're going to stay there. But the point is, you can see that I can push this thing in another direction, and it'll just collect force arrows in those directions. And that's all. It'll just collect them in the empty space. And you can sort of see that the 3 dimensions are 3 different dimensions around the object. I don't know exactly how to draw that, but you know, the 3 dimensions are realized as 3 places of orientation to my neighbor. I can be oriented to my neighbor this way. I can be oriented to my neighbor this way. I can be oriented to a neighbor this way. And you collect force in those arms. And that is where you gain your material velocity. Velocity is a material function in the sense that the tons, it's velocity, but it's an elemental velocity. So again, the speed of light is elemental. It has to do with the basic elements of the function of the system. The basic element is force. All of the forces moves a certain amount of distance in a certain amount of time. And I mean by certain, definite amount of time. Alright? And that's it. A Planck distance and a Planck moment. And they all do exactly the same because they're all elemental. And that's the function. So that's the context of what I'm talking about. That's why I'm saying it makes no sense for light when it's the same as the other tons. It's same as graviton, same as magneton. I'm saying basically that the gravitons are converted into magnetons. They're exactly the same tons. They're just propelled out in volume. They're segregated by a magnet. A magnet merely says, all the blue ones up there, all the red ones down there. Same exact tons. It just tells the force tons which way they're going to align. They're going to align on these spokes, and they're not going to align on these spokes. Kind of a thing. And that creates a polarizing filter. Yeah, and so light's the only exception. And what we have as evidence for this only exception, this one and only exception, and the only evidence you people have is silly thought experiments and crappy lensing images. And that's it. That's the only evidence. It's crappy evidence. And so clearly I'm going to argue to you or plead with you, well, scrutinize that evidence. Recognize that you're the ones breaking something elemental. You're the one saying this elemental element can carry velocity in 2 dimensions. I'm giving you a reason things have inertia, because they're carrying actual force. This thing can't carry force except in one direction. It can't. It's not possessed of the mechanism to do it. It doesn't have that tool. It doesn't have that function. So yes, I'm just saying that this relativity crap of perception is so irrelevant. There's one factual reality. How it is calculated by machines not functioning. I mean, I try to do the frame rate argument because I think it makes sense. It should make sense to you. That all you can do is change what the thing sees in terms of frame rate. You can't change what actually, like, whether something bends or not. You can only change whether I see this thing go away from me at a certain speed. Well, that can happen based on how fast you blink your eyes. But you can't change its direction. If something's moving in a certain direction, it's moving in a certain direction. And even in their silly observer experiment with the mirrors and the bouncing light, the observer's seeing the ship moving. He's not fooled. Alright, anyway. Alright, well, I guess I'll do this now, just to pose it. You know, because some people won't bother listening to the rest of the video, so I'd like them to understand the small augmentation I'll make to the thought experiment. Alright, so you have the light gun. The ship's moving 1/2 the speed of light. The idea is you've marked perpendicular. There's a hole right here where perpendicular is. The idea is the light's going to go through the hole and out of the spaceship. I'm arguing the only way you can do that is you have to put the hole back here. They're arguing that it will go straight across right into the hole. And so what I would change the experiment to is, let's just put the person here and he's going to watch it. So he's going to just watch it's a smoky room. He's going to watch the laser beam go through the hole. So he's standing here. Now, an observer out here is going to see what? He's going to see the beam, by your theory, go this way, hit this guy, and light him up. So he's going to, it's a dark room, and he can't see this guy unless the laser hits him. He's going to see the laser hit this guy, and it's never going to go through the hole. The guy in the ship is somehow going to see the laser go straight across and go right out the hole. I'm saying what's going to happen is the laser is going to go straight, but the ship's going to move, so the beam will go perfectly straight, the ship will move, the hole will be right where it's supposed to be, and the light will go right through. No, I'm not saying this. The hole will only go through if you move the hole backward. So obviously the light will hit the spot behind the hole. So there's a spot on the wall, the light will hit that spot. It will never go anywhere near there. And the observer will see the light appear to I mean, he won't see it as, I'm arguing, I don't think he's going to see it as a bend. He's going to just see it make a straight line right through the hole. And the direction, though, I guess this is almost like a, Well, the point is when the light finally gets to him, it's going to be straight. So the beam will actually go out here, because by the time the light gets to here, the hole will be where it's supposed to be, the spot. So there won't be any illusion. Right. So when it continues on its voyage, if this was a second hole, it will continue on its voyage in the correct direction. The light will do one thing. It won't do two. I should have just stuck with the little guy and just said, go ahead and explain how your theory works if the guy's standing here. Yeah. So it just depends on where we put a block. Will prove one of us right or wrong. But I'm just saying there's no theory then. You're saying that the light is going to hit that person. And the observer on the ground is going to see the light hit that person. No way. Alright. Yeah, there's not. I've already made the argument about you can't change the fact that it's a longer line. By my argument, it's not a longer line because the ship is doing the moving. So the light just goes straight across and the hole shows up and the light goes through it. And that's what the observer sees. Yeah, if he's looking at the light. Just ignore the damn ship and just look at the light. That's what you see. Because that's what will happen. Okay. Alright, so then we'll play some of this in this context of the pre-explanation. Let's see, what computer am I using? I guess it's this one.
For the consequences.
I mean,
It's light.
I skipped over the unnecessarily useless blah blah blah. Yeah, the whatever gratuitous insulting portion of the programming. Again, they keep claiming that you know that I'm the one who instigates the poor quality of the rhetoric. And again, the only thing I add is the more colorful language. You know, I'm a Clarence Darrow, I mean, I believe we should use all the words in the language. So I'm not going to play a game and insult somebody with a little fancy pants bullshit rhetoric. I'm just going to say asshole. Asshole.
Doesn't leave with a momentum component in that direction. Then you're kind of saying that you could use light, you know, powerful laser as a spaceship braking mechanism, perhaps.
Okay, so this I couldn't make any sense out of. He's saying because I'm saying light leaves and it's just released. That's all the electron's doing. It's just saying, see ya. And the light goes all by itself. It has the speed of light all on its own. It doesn't propel it. It doesn't push it. It doesn't give it force. The light already has it. It's just releasing force. It's releasing something. It already wants to go. It's already bouncing back and forth, and all you're saying is, go. You're letting it bounce one last time, and see ya. No force involved, no energy involved. Just force is involved in the sense you're releasing some force. You've stored some force, you release it. That's a photon if it's at a frequency. It's a magneton if it's polarized, and it's a graviton if it's random. Alright, so he's saying that because light doesn't carry momentum, I can break a spaceship by pushing light out the side of the ship. Well, you can break anything by disposing of your force, getting rid of it. So, yes, you could argue that any way you get rid of it, like shooting any energy forward, you could get rid of it.
You pump out lasers to the side as you approach the galactic, you know, or some of the solar system, and you know, as you've accelerated, you would decelerate because you would pump out the energy. You know, M equals MC squared. Get down, you blend.
See, but it's not energy equals MC squared. This has nothing to do with mass. Possessing force will not necessarily increase your mass. It's not, let's see how to say it. It's mass in one direction. it's unidirectional mass. So that's what I've tried to argue too. So I've emphasized this point that I would give a ton a unit value of 1. It's the 1. So if I collect force, like the space shuttle, so wherever you went, where did the space shuttle go to? Oh, here it is. If I give a bunch of force arrows, it has a bunch in this direction. So it's gained mass only in this direction. It's only gained arrows in this direction. It has not gained mass in this direction, or no, certainly not in that direction. Seems to have lost some in that direction. And so in all the other dimensions, it has not gained technically any mass. See, atomic weight is your three-dimensional weight. That's your total weight in all 3 dimensions. So you have to be really careful when you're talking about mass, because your mass can be moved, it can be flipped directionally. Now, the electrons can't function if they give up too much of it, their force. Again, they're not electrons or protons, so they have a limit, they break. And so there's a certain speed that will break the electrons and the protons. And certainly I think we have some evidence of that in accelerators, and that certainly material bits break early, and then the nuclear bits break, and that's why they see all the crap they see, is because they're really throwing parts at things.
And we're reducing your net velocity, net momentum, which would correspond to a loss in velocity.
Well, yes, if you shoot out your force energy, release it, but releasing it sideways, you'd have to convert it. But I'm just saying, any way you release the mass of arrows you have, you still have to get rid of the ones going forward. So shooting them out sideways, I don't think will do it. I mean, there might be some theory where that's possible, but I haven't, you know. The simple thing to do is shoot it forward. Then you're getting rid of it forward, which means you're going to change your balance because you're getting rid of it. Seems obvious to me. Which would essentially constitute an exhaust in the forward direction, which is pretty much how spaceships slow down.
So, yeah, it's not going into the future. It's just...
Well, they actually spin, which is so cool. They spin around and then shoot it backwards. The force stays in the same direction. The physical ship turns, the shell. The force has stayed the same direction, and then they shoot the exhaust out the front. The back that's now the front.
So it's off the direction. And this is part of the reason, yeah, the little documentary about frames of reference from the rock.
Okay, so this is another thing where, you know, I'm doing physics, okay, and he's talking about like almost chemical. It's worse than chemistry. I mean, it's mechanics, and I'm not saying mechanics doesn't completely dependent on physics, but I mean mechanics at 5 miles an hour has really so little to do with this stuff. And it's all hard matter he's talking about. You're talking about matter interactions with matter that have little tiny bits of force between them. And so it just doesn't get to the heart of it. I'm not saying I'm totally informed now. Now that I realize what force is, I can watch these interactions between these frames, so to speak, of reference, and I can better understand that something's injected with a force, and the force has to leak out somewhere. There has to be a place for it to go, and all this kind of stuff, so I can see that so much better. But again, that video has so little to do with this part of physics. It's really just comparing kumquats and watermelons.
White film uploaded not so long since.
Alright, this was an insanely long pause. I mean, I got to speed it up and it's too long.
So that was a puzzle. you propose a kinetic, particulate, quanta-based time universe, and you can accept that a baseball, when released, within one frame of reference, within the train, looks to go straight across the carriage, but in actual fact, it's from the external frame of reference, travels the diagonal.
Right, at a higher velocity. A combination, essentially, of the two velocities will hit the person catching the ball. And if we reverse the situation, is essentially what we're talking about. So, right, here he's going to talk about it, but you should have reversed it, right? Because we're talking about essentially hitting moving trains now. We're talking about what's happening on the moving train, not what's happening on the ground guy. So the ground guy is more irrelevant. He's the thrower, so to speak, like the light gun on the wall. He's just initiating something, and we're seeing what happens after it's initiated. But clearly, if you were trying to throw it to the person on the train moving, you would have to lead them quite a bit for the ball to make it to them. So you would have to throw it into the future, where he will be, not where he is.
But with your postulates of this quanta nature kinetic theory, somehow you have a problem with the idea of a photon of light being released, and it also from its trajectory and being dependent on the frame of reference. And
it's not about being dependent on a frame of reference. It's about carrying momentum in more than one direction, carrying momentum in more than one dimension. I have explained that matter can do that. Matter has the capacity to carry the force that will allow it to have velocity in different directions. A ton can't. It has no mechanism. It is an elemental particle. It has an elemental function. It cannot do anything else but go straight in one straight line. It can't go straight in two lines, in two ways. It can't go the speed of anything in the other directions.
That it truly actually sets off with a component in the other direction. It's not bending, it's not going into the future. It just set off straight as an arrow in that direction.
Well, again, I'm just saying, if the thing you're hitting is moving, that won't hit the thing moving. You can't hit a thing moving, okay, by shooting a photon straight.
Perceived to be perpendicular, transversing the train, by a person in a train, in a spaceship.
I'm just saying, all these thought experiments are dependent on a breaking of somebody's perception, but we should be able to agree that only one of these physical realities happened. So again, if I place the person here, we should be both able to agree it either hits him or doesn't hit him. It can't do both. So either one of us is right and one of us is wrong. There's no way to get the one. You can't say, it both hit him and didn't hit him. So I'm just saying you're stuck with there's a right and a wrong answer. It either does or doesn't. And I'm saying I'm voting for doesn't. Clearly, loudly. I guess the point is they've set up the thought experiment and they created two wrong observations. They create the wrong observation of the guy on the spaceship, and then they had the wrong observation of the guy observing, because I don't think they saw what really happened. He doesn't see the light go forward. He sees the light go backward and hit the wall. So they created two false characters doing something that isn't the third option, which is the truth. So they make their two options fit each other because they reversed which way the light had to go. The observer doesn't see the light go forward. He sees the light go backward.
I was in error a few weeks or so ago in conversation with Trick, and I didn't. But Pyro also took Trick's position that two people traveling in spaceships both observe each other's clocks to go slower.
Both observe each other's clocks to go slower. So you're saying that, well, you both see the same time because you're both going the same speed, so you have both the same broken clock. So yes, you can look at mine, I can look at yours, and they're going to say the same thing, which is we're fucked, because they're going to look out the window and see light moving the real speed of light.
I thought there was an intuitive consistency where if one person saw one's clock go slow, that the natural inverse was true. But I've forgotten the very principle of relativity, and that was there's no preferred reference frame, so it does appear. From one person's point of view, he's stationary at constant velocity, and the other person is flying. This is a problem for Remendum, I think, because he forgets.
I don't forget anything. This is just such an obnoxious way to argue. He hasn't learned, he has forgotten, he is this, he is that, because I am right. Oh, well, I'm saying I am right. So again, this is just, you don't understand how this is just the way you provoke an argument. This isn't how you respond to a point. You have a different opinion. Okay, well, what do you base it on? What evidence do you have for your different opinion? All the scientists say so. They all think dark matter exists, so it must exist because that's what they voted for. Silly putty.
Nick account when he places his I think this is a possible problem anyhow. He forgets to take account of moving his mental abstract.
I know. I continue to say there's no frame, so I'm saying your whole premise of a fucking frame is bullshit. What I'm saying is your matter's degrading. Your eyes are blinking. This is the idea, okay? When you're standing on the ground, not moving, no velocity. You're the space shuttle on the ground. Your eyes are blinking so fast you don't see the blink. You're seeing reality. And then once the shuttle starts taking off, your eyes start blinking slower. And now you're taking in less of reality. And that's all that's changed. Okay, if a bird's flying, I was seeing a bird fly. Now you're seeing bird here, bird jumps to here, bird jumps to here, bird jumps to here. Because your frame rate is fucked up. So everything looks like it's going faster because you're not seeing all the frames your brain has cut out. So it's just like me speeding up this video. I'm just going to see less video in the same amount of time. And I'm going to think everything's way too fast because I'm seeing less in the same amount of time. That's the wrong way to say it. I'm seeing less. Yeah, I'm seeing less in the same amount of time. Right. Because the single frames are on the screen longer. You could say it that way. I think you could. But it doesn't matter.
Frame of reference in thought experiments. And considering that, yes, if you shoot a beam of light from you, say it's one light year to the next star system, and you're halfway there, you switch on your lights, and halfway there, it takes half a light year for the light to get there. Well, if you were doing half the light speed, it'll still take you a quarter the time to get there. So in terms of
it doesn't change your speed, it just changes the time of arrival of the different elements. But no wait, the light never changes. The light is the constant. It's called the constant. I know that doesn't mean anything anymore, but that's what it is.
The person left on Earth, and when you return, that journey still takes the conventional times. But what you will measure, if it's in thought experiments.
Well, exactly. That's the whole point. It doesn't. Your measurements are just bullshit. That's all we're validating the fact that you don't have a working clock and you think everything's. Hey, I got plenty of time. I got plenty of time. My clock is barely moved. I haven't used up any of my time, and I'm back on Earth. Yeah, your sister already got run over by a car, and everybody you knew is dead, and blah 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 blah.
But at least is that the light will leave you. light speed because your clock's running slow.
Well, the clock changing the light thing, I'm still going to argue that well, first off, you can't really perceive light, can't see it. So we're saying if you could see the tons, yes, you're going to see the tons moving faster than the speed of light as you break U. Light is going to go faster. That's because you're broken.
An external observer will see you, will see the light. I think this is very unintuitive. I think an external observer sees the light leave you and sees that you're doing light speed, half light speed, and sees, that probably there must be some trouble measuring it. I can't quite make sense of it.
No, there's no problem. He sees the light leave at light speed, and he also sees you moving half the speed. So he just sees two runners, one going 30 miles an hour, one going 15 miles an hour. There's nothing complicated. It's like they're running. They were behind. One runner was behind a building, and so they come out from behind the building, the 30-mile-an-hour guy. So you can imagine him emitting the light. So the 30-mile-an-hour guy is he's going the real light speed, and the other guy's going half. So the 30-mile-an-hour comes out from behind the building and from behind the other runner, and he's going 30 miles an hour, and the runner's going 15, and that's what the observer's going to see. It's not complicated. The observer's clock is working, so that's the difference here. These aren't just relative positions. There's one who's got a working clock, and the other asshole's broken. The observer's always right. The idiot is the one fucking it all up. And I'm saying there's certain thought experiments, like I said, when you start doing this perpendicular thing, that's when you're not going to have an ability to make choices, rationalizations to say why somebody sees it different. There's an absolute fact. The light either hits this fucker or it doesn't. Now the observer, isn't going to see it hit him unless you put it on the other side. So if I put the observer here, watching the beam, the guy observing is going to see the light smash into the asshole in the way. There's no other way it can happen, because he's standing in front of the beam from the observer's perspective. No, he's not standing in front of the gun. He's standing in front of where the light's going to end up going. Like I said, it goes in pieces to the destination, in the sense that the first photon is going to be in one position, the second photon is going to be in a different position, the third photon is going to be in a different position. And they're all going to hit a moving target. So they're going to hit the same place, but they're obviously going to hit the same place in a different sequence. So they're going to hit it from a different location. So the first one will hit it in one place. The next one will hit it in another place. The next one will hit it in another. I probably should be doing this the other way around. The first one's going to hit, and then the second one is going to hit the move spot, and then the third one's going to hit the move spot, and the fourth one's going to hit the move spot. They all traveled straight from where they were fired and where they ended up. Well, whatever. I should have drawn it, but we've already been over it. The point is, there's one thing that happens, and I'm saying the observer's the guy who sees it right, and the broken perception guy is seeing it wrong. And I think the physics necessitates recognizing the fact that the ship is moving.
Perhaps somebody could offer in the comments what an external observer. See, there's a timing problem. The external observer may well time and say, see, you can't measure the light.
Well, look, the whole observer thing gets so messed up anyway, because if you make him moving, if he's moving the same speed as you are, well, then he sees everything like you see it. If he's moving the opposite speed, then he sees it twice as wrong as somebody stationary. And so then you make the lights not even moving or something. That's where you get into this problem where you start breaking the sequence of events. And all of a sudden, spontaneous, or coincidental events, what's the word, instantaneous events are no longer perceived instantaneously. It's just stupid.
You'll see it not leaving you as fast, But if he was any way of measuring it, he would measure the speed of light, and reading you at the speed of light. Okay. Anyway, let's ramble off. I've said all that needs to be said.
All right, well, that's all you got to say on the subject. I'm just saying you set up a circumstance whereby your description of what light does, which is carry two momentums, I can make light move faster than the speed of light. That's the implications of it. That's the implications of the baseball. If the baseball has two momentums, it will arrive at the location with a speed greater than any of those two momentums. The two will add up to a new vector with new intensity. So that's the implications of this crap.
This is approaching a close. I just got a bit of time on my hands before I set myself some goals, personal goals in maths, physics.
Yeah, whatever. I'm just saying I don't think you've answered the questions, and I my questions certainly, and that's like I said, this isn't all productive anyway, but to just leave it and say, okay, this momentum thing isn't important. No, this is the foundations. It's a foundational axiom, and you say you have hard evidence that light carries momentum, and I'm just saying the implications of that is that nobody can ever talk about seeing planets as they were, because you're seeing them as they are, because the light's moved with them. I mean, there's just so many implications of light carrying momentum. The sun's rotation. Okay, so the sun is actually producing light that is moving a little bit faster than the speed of light, because it's curving to hit us, like a baseball.
Other things. So I consider myself regretful, perhaps. I come across too sarcastic and condescending as I carry on, a run-on feeling from our ethics debates. But yeah, I mean, if I can make a quick contribution, maybe I'll keep making videos. It's not taking that much of time.
Yeah, well, whatever. The quick contribution will be saying, you said velocity instead of acceleration. This is going to be, I caught you with a typo. But anyway, yeah, I mean, if you can, this again, you just say, this is the kind of rhetoric that's totally unproductive. All right, momentum theory breaks conservation of momentum. Now, was there anything in here that demonstrated how I'm breaking the conservation of momentum? I can't make arrows disappear. I can't make force, I can't make energy just pop into existence by bending some space or something. I have to account for it. It has to all go somewhere. Where am I not accounting for it? Where am I allowing the arrows to just go away, fly off somewhere, and not have a consequence? So it's just bullshit. It's a bullshit accusation that I'm the one breaking conservation. And I'm the one preserving the speed of light. I'm the one saying the speed can't be increased. You can't give light extra momentum, and therefore in another second direction, which always has the implication that the net velocity will be greater than any of the two velocities. There's no choice. And that's the implications of what you're doing. You're breaking conservation, not me. But I'm just saying, if you're going to title videos with this kind of bold statement, you ought to have something called something near a hard piece of evidence, something like it. And there's no hard evidence anywhere in this crap. And this whole conversation, I'm just keep showing you places where there's just no hard evidence of any of these conclusions drawn. Lensing, where's the hard evidence? Doesn't exist. Where's the great image? Doesn't exist. Where is the triangulated image? Doesn't exist. We don't get anything. We get little crappy, fudgy pieces of evidence. Anyway, and then the other subject, what I wanted to point out what the evidence was for that. Damn, I forgot this. Dark matter. Zero evidence. The evidence is it fixes our broken math because we can put it anywhere. It's really cool. You want to fix a problem? Just smear the dark matter on. You don't have to obey a single rule of conservation. You don't have to obey any rules of logic. You just stick some there. Anywhere you need it. Universal fixie. Pixie dust. Anyway. Alright. So that's probably enough. I think, but look, this is like I keep saying, this isn't that complicated. I've broken the universe down to this simple thing of force and electrons and protons. I haven't even had to talk about neutrons yet, but I'll get to them. But they're not, they're just part of the mechanism that holds the thing together, so a bunch of force can go flying between these things without everything flying apart. And that's probably all they are. They're just like little magnet bars that hold the protons and prevent them from going wacky. Because they really hate each other. Electrons hate each other, but protons really hate each other. Alright, anyway. Till next time.